Okay, so let me start by thanking the organizers for giving me the opportunity to speak here. I'm going to talk about inertial run-and-tumble particle, and this is based on ongoing work with Debraj Jotto, who is a PhD student in my group, and Anupam and Sanjib, who are both here. So we have already heard a lot about active particles in this meeting, so I'm not going to speak about this too much. Just to recap, brief thing is that so when the particles, these active motion are found over multiple length scales, both in nature and also in lab. And while for particles of the size of micron, it suffices to describe with them, their motion are mostly overdamped. But inertial effects cannot be ignored if the particles are bigger, if they are macro sized of the order of millimeter or centimeter, like these vibrobots or hex bugs. And recently there has been a concerted effort to characterize effects of inertia in active motion. However, there are still many questions which are unanswered. So yesterday Mamata talked about inertial AOUP. And today I'm going to talk about another well-known active particle model, this run-and-tumble particle, and what happens when we include inertia in them. So this is the model. So because this is an inertial particle, we have both position and velocity. So x dot is v, and then the particle can be in some general external potential ux, is a dissipative force, and this is the self-propulsion force, which is the RTP type. So it's a dichotomous noise. It changes direction with some rate alpha, and unlike the overdamped case, the change in this force changes the acceleration of the particle. So we'll take the simplest case where the external potential is just a harmonic trap with coefficient mu. So what we first notice is that the Langevin equations can be recast in this form for a harmonic potential. So if you look at it, when sigma is constant, this is nothing but a damped harmonic motion of a deterministic particle in a trap which is centered at this A0 mu by sigma. So when sigma switches, the trap minimum switches. So it's a bit similar to what Sanjib talked about yesterday, but we are talking about inertial particle and just one particle, and how the behavior changes with respect to the overdamped case. So it's good to just very briefly recap what happens when we have a massless particle. That's the overdamped RTP that all of us are familiar with. So this has been studied in a lot of details, and particularly the behavior of this particle in a trap has been explicitly calculated by Anupam, Abhishek, Shotto and Sanjib and Gregory. And what they showed is that this particle, the position distribution is bounded in this region for a given propulsion strength A naught and trap strength mu. And the position distribution shows a shape transition as one increases the activity. In the passive regime, it's a bell-shaped curve, like a Gaussian curve, and in the active regime, when alpha is smaller than some critical value, it has a U-shaped curve. So the particle likes to stay away from the origin of the trap. So here we are going to talk about what happens when we have a finite mass. So it turns out that there are two different regimes. So similar to the deterministic particle, we have an overdamped regime and an underdamped regime. So the oscillation, the motion of the particle is very different, and it also shows up in the distribution of position and velocity, which I'm going to talk about next. So the first thing that we found is that in the overdamped regime, so the boundary of these regimes are given by this. So gamma square greater than 4m mu, same as the deterministic particle, this is overdamped, and when gamma square is less than 4m mu, this is the underdamped regime. And in the overdamped regime, in both cases, the position and velocity have a finite support in the phase plane. And for the overdamped case, the bound for position remains same as in the usual massless particle, whereas velocity, now we have a velocity. As soon as we have a finite mass, there is a velocity, and that has a bound, which is also mass independent. But once we move to the underdamped scenario, now the bounds change and they start depending on the mass. Okay, these are some exact expressions. You don't need to remember the expressions, only that depends on the mass. Now let's look at the underdamped scenario a bit more closely. So this is the position velocity distribution. Okay, so what happens is that in the underdamped regime, the motion is characterized by two time scales. One is the inertial time scale m by gamma, and then the activity time scale alpha inverse, the inverse of the flipping rate. And as the relative strength of these two time scales change, we see a transition. So in the strongly active regime, when tau a, the activity time scale is much larger than the inertial time scale, we have this strange shape which goes over to the more common Gaussian shape in the passive regime. So to understand this a bit better, we look at the marginal distributions of position and velocity. So look at this blue curve. This is the most active scenario. Alpha is 0.01, which is much smaller than the other parameters. So we have a strange multi-shaped, multi-peaked shape. And also for velocity, we see a multi-peaked shape, which has not been seen for overdamped particles. I mean, in any of the active particle models that we know of. So how do we understand this shape? It turns out that we can actually understand it very simply by just considering the deterministic motion. So what happens in this range? So alpha is very small. So the typical time between flips is much larger than the relaxation time scale. So when I mean the motion of the particle is that it sits in one center of the trap when sigma is constant, and then when it flips, it tries to go to the other minimum, and it reaches the other minimum before the next flip happens. So basically it just traverses between the two minima, okay? And so the dynamics can effectively be described by a deterministic process where this flip happens at a regular interval of alpha inverse. And if we actually simulate this process, it turns out that this effective process quite accurately describes the position and velocity distribution that we get. So here the dashed lines show this distribution from this effective process, whereas the symbols are the actual process. And we can actually calculate the position of these peaks, which are nothing but the turning points of this motion. So here, when the particle crosses this v equal to 0 line, it becomes very slow and it spends a lot of time in that position, which gives rise to these peaks. And for the velocity, this is where the acceleration becomes 0. It spends a lot of time in that velocity, giving rise to these peaks in the velocity. Okay. And now we go over to the overdamped scenario, and in that case it turns out that there are three time scales now. One is the inertial time scale as before, and there is a trap time scale gamma by mu. Tau 1 is always smaller than tau 2 for this overdamped case, and there is of course the active time scale. And in this case what we see is again a shape transition, but a very different kind of shape in the strongly active regime. So here we have three different regimes. In some sense we have strongly active and a moderately active regime, where the activity time scale sits between the two other time scales, and then we have the passive regime. So the most interesting is of course these two, and it turns out if we look at the position distribution, then it's qualitatively very similar to the massless case. It goes to a well-shaped curve from a U-shaped curve, but the critical activity now depends on mass, and we can calculate it to leading order in m by gamma. But the more surprising thing happens if we look at the velocity. So the velocity actually undergoes two different shape transitions. So in the strongly active regime, we have an algebraic peak around v equal to 0, which goes over to a double peak shape in the moderately active regime. So these peaks are basically around the critical speed. And then if we decrease activity more, we go over to the passive regime, where we again have the, I'm almost done. We have this bell-shaped curve. So just to conclude, so we have looked at this effect of inertia in run-and-tumble particle, and we see that the presence of this finite mass gives rise to emergence of two different regimes, underdamped and overdamped. And this underdamped, in both cases, the presence of mass gives rise to strange shapes in the position and velocity distribution, and we have some analytical understanding. It's a work in progress, so any input is welcome. Thank you all for listening.
Questions?
I guess in this problem probably one can compute cumulants exactly, right?
Cumulants, possibly. We have done the stationary cumulants up to. So we actually calculated the deviation from Gaussian by calculating the cumulus up to 8th order or so. Okay. But we also have some analytical expression for example, for this first transition, the velocity distribution can also be calculated analytically, and the transition point, etc., can be found. RG.
If you are able to calculate the cumulants, you can also able to calculate the RG equation. Okay. RG equation is nothing but the higher order, particularly the part-derivative RG.
Okay, great.
So let's just thank the speaker once again.